Okay, welcome to the next video. Here's the next bigger idea. We're going to write a polynomial, a Maclaurin polynomial for a function in this form, 1 over 1 minus x. What does this have to do with sine and cosine? Nothing, actually. So let's look at it a different way. Remember when we were looking at the sum of a geometric series? We know that the sum of a geometric series is written in the form of a over 1 minus r. Well, if you'll notice, this function that I've given you is also in that same format, where this is a, the first term, and this is r, which is the common ratio. So I can use that idea to write a Maclaurin polynomial for 1 over 1 minus x, because I know the first term. And then remember, this is a series. When I'm finding this is the sum of a series of numbers. So the sum of the sequence. There's addition in between each of these values. So if I add up this infinite set of numbers, I'll get a over 1 minus r. So the first term in my series is a. That's 1. To get to the next term in the series, I'm going to have to multiply by my r value. So I'm going to multiply by my r value, which is x. 1 times x, that's x. And I will multiply by r again. So that's x squared. I multiply by r again. I multiply by r, and so on and so forth. And then what would the general term be then? What would the general term for this be? It would be x to the power of n. N equaling 0 first, and then n is 1, n is 2, n is 3, n is n. Kind of cool. So this looks like the sum of a geometric series. Using that idea, we can find a Maclaurin polynomial because we know the first term and we know the common ratio. I want you to graph a couple of these polynomials against 1 over 1 minus x, because we saw with sine and cosine that those polynomials that we were writing fit those functions pretty well. I would like you to graph, Desmos, your calculator, whatever. I would like the first one, so y1 to be 1 over 1 minus x. And then y2, I want it to be the first couple terms of the Maclaurin polynomial. And then add on a lot more terms. How good of a fit is this polynomial for 1 over 1 minus x? I hope you're graphing it. What we can see for these polynomials is that no matter how many terms we have, it's only a good fit for values close to 0, because this Maclaurin polynomial is centered about 0. So the Maclaurin polynomial centered about 0 is only a good fit for f of x equal 1 over 1 minus x near 0. We were finding for sine and cosine that the Maclaurin polynomial we were finding was a good approximation for sine and cosine for any value, because the more values we added onto our polynomial, the more it just fit that sine and cosine curve perfectly. But when we get into a case like this, the polynomial we're finding only converges to 1 over 1 minus x for values really close to 0. Okay, I want you to go on and try a couple more. I'm going to ask you to write third-degree Maclaurin polynomials for these functions. And I want you to pause, and I want you to go try this on your own. Okay, welcome back. The first three, not too bad. The first three kind of look like the sum of a geometric series. In this case, we know that the first term would be 3, and here's the common ratio. The common ratio is 2x. So I can say that f of x will approximately be the first term plus 3 times 2x plus 6x times 2x, and so on. Graph these. Oops. We're not going to worry about the general terms right now. We'll just say plus dot dot dot. Graph this Maclaurin polynomial and graph 3 over 1 minus 2x. I want you to look at convergence. We're going to determine exact convergence intervals in the future. I just want you to start thinking about it now. How good is this polynomial going to emulate the function that we're looking at? So how good of an approximation will it be? Okay, on the second one, we need to do a little bit of rewriting first, because this isn't quite in the form of a over 1 minus r. So here's a, but this is 1 plus x. I'm going to write this as 1 minus r, like that. So now we know a, the first term is x. We know r is negative x. So in a polynomial that could be an approximation for this function is x minus x squared plus x cubed minus x to the fourth, and so on. Okay, let's look at number 3. Number 3 also kind of looks like a over 1 minus r, except this is not in the form of 1. So what we need to do is divide both the numerator and denominator by 2. That way we can write it in the form of 1 minus r. Okay, to do that then, this becomes 2. And this becomes 1 minus 1/2 x, because I have to divide everything by 2. So now here's a, here's r. I can write a polynomial that's a decent approximation. So a is 2. And then 2 times 1/2 x is x times 1/2 x is 1/2 x squared. Okay, last one, and this one is the trickiest. We know, or we can find, actually we know, we did it already, the polynomial for 1 over 1 minus x. We know that that's 1 plus x squared plus blah, blah, blah. We also know that if we find the antiderivative of 1 over 1 minus x, this is almost in the form of u prime over u. So the antiderivative of 1 over 1 minus x is the negative natural log of 1 minus x. We're looking for the natural log of 1 minus x. So the negative natural log of 1 minus x is equal to the antiderivative of 1 over 1 minus x. So let's do some replacing then. We have a polynomial for 1 over 1 minus x, so if we find the antiderivative of 1 plus x squared plus x cubed plus x to the fourth, then we can find the antiderivative of all of those. So that's x plus 1/2 x squared. And then in order to solve this, to actually find the natural log of 1 minus x, I'm going to multiply both sides by a negative to make this a positive natural log of 1 minus x. That's what we originally started with. Here we go. So it's all about being creative with things. Oops, those should have been minuses. It's being creative with the things that we do know in order to find polynomials for things that we don't know. It's going to be up to you to be a little creative with these things. Okay, I'm going to let you go. Go see what you can do, and we'll talk about the homework later.